Hi, chemistry students. I want to talk about a mechanism and essentially do a case study on it. It'll be a couple of videos. The first video here is going to be focused on the first step of the mechanism that's given to us so we can understand this concept of equilibrium a little bit better. So the big concept here that we have is that we have a reaction, which is two NOs plus an O2 reacts to make two NO2s. This reaction is given to us and we're told that it's a bulk reaction. Because we know it's a bulk reaction because someone has proposed a mechanism. There's a proposed mechanism for it right down here. So only a bulk reaction would have a mechanism for related to it. We are told that it's experimentally found to be second order in NO and first order in O2. So we could write a rate law for it. We're not interested in that right away, but we will a little bit later. So the overall question is going to be, is this mechanism valid for the proposed for the reaction? And we'll go into that in the next video, but this first video is really about this whole idea of this first step. What does it mean? What's it all about? So let's take a look at that real quickly. So here's that first step, kind of naked and stripped away from the rest of it. If we had only seen this, we'd be learning about a new thing called equilibrium. And equilibrium is, we've experienced it before, when we were talking about vapor pressure. When we talked about vapor pressure, if you remember, we said that that was when the rate of evaporation was equal to the rate of condensation. So whenever there's an equilibrium, there are two opposing or opposite directions of some sort. In this case, evaporation versus condensation, two opposite processes it can be. And these two processes, if they happen at the same rate, we're going to call that equilibrium. Well, that's what's happening here. What we're saying is we can imagine this reaction happening with a rate constant K1 to form N2O2. But we also can imagine this reaction happening, N2O2 breaking apart with a rate constant named K-1 into NO plus NO. So both of these processes can happen. And if you think about it, if we started with only NO, then the only reaction that can occur initially would be to create N2O2. But after a while, there will be N2O2 in the container, and it can start to break apart. So as our pile of NO2 of NO, so here's our NO pile, as it dwindles and slowly goes down, our pile of N2O2 will start to go up. And at some point, their concentrations will be just right. So at some time, the concentration of NO and N2O2 will allow the rates to be the same. Well, what rate am I talking about? Well, I'm talking about the rate of this reaction, the formation of the N2O2, and this reaction, the decomposition. So in other words, we're going to have a rate of a forward step. This is the forward step. The rate forward will equal the rate of the reverse step, where this is the reverse step. By the way, the reason that this has a -1 in its little, in the way we've symbolized it is, it's part of the first step of this mechanism, and I'll show you that again. See, this is the first step, step 1 of the mechanism, step 2 of the mechanism. It's part of that first step, but it's the reverse, so we give it the -1 symbol just so that people know that's the reverse step. All right, so let's go back over here. We've got the rate forward is equal to the rate reverse, but these are elementary steps. How do I know that? They're in a mechanism. So every reaction in a mechanism is an elementary reaction. That being said, I can write from the stoichiometry exactly what's going on. So for the first step, for this step 1 right here, the rate forward, we know that that's going to be K1 times NO, and there's two NOs, so it's going to be NO times NO. That just means NO squared. And that's our rate forward. Our rate reverse is equal to K minus 1 times N2O2. And this is a new little relationship that we have between the concentrations of these. When we reach its equilibrium, where the two rates are the same, we have at our disposal this relationship, which is just a bunch of symbols that can be mathematically manipulated. Let me show you how that can work for us. So what I'm going to do is I'm going to move this up and get a little bit more room so we can play with this, this one equation right here. And all I'm going to do is rewrite this, and I'm going to try to make this ratio happen. I'm going to try to make a ratio of the forward to the reverse. I want to make that. So to do so, I've got K1 NO squared is equal to, I've got to have a little more room than that. I've got K1 NO squared is equal to K minus 1 N2O2. So I'm going to divide, my forward is my K1. So K1 in this case is equal to my forward rate reaction based upon the equilibrium, the way it's been set up, and K minus 1 is my reverse. So I'm going to divide both sides by the reverse. I'm going to divide by K minus 1. And of course you see that those cross out. But I'm going to also do one other thing. I want to isolate my K forward over my K reverse. So to do that, I need to get rid of my NO squared. So I'm going to divide both sides by NO squared. And here we see those cancel out. So when we're finished with this little bit of algebra, we find that we get the forward rate constant divided by the reverse rate constant is equal to the concentration of the products divided by the concentration of the reactants raised to their stoichiometric coefficient. And we've created a new thing called an equilibrium expression, which is just a relationship, a mathematical relationship between the rate constants and the concentrations of the species involved with the equilibrium. That means we can just rearrange this because this left-hand side is constant, because this is constant over here. That means we've got just mathematics we can do here, and we'll use that when we solve for our, when we try to finish up our mechanism and make it work out for us. So that's what this is all about. We wanted to get to the point where we understood this whole concept of equilibrium.